We saw in the last video that when dealing with straight chain alkanes that we can get free rotation around the single bond, and I'll re-show you the example we used of ethane having free rotation about this single bond, causing its hydrogens to rotate along the circumference of this carbon. So the next logical step we should ask ourselves is, how do these conformations due to free rotation around single bonds manifest themselves in cyclic compounds? And we got to remember that there's a fundamental difference between straight chain compounds and cyclic compounds, and I'm going to show you that difference right now. This is how we draw the compound for cyclohexane. This hexagon, this hexagonal shape represents at each point a carbon, and you can count 1, 2, 3, 4, 5, 6 carbons, and each one of these carbons, like I've shown you before, has 2 hydrogens attached to it, one here and one here, and so each carbon does indeed have 4 bonds, but the hydrogens are implied. Since, and you can observe this for yourself, each carbon on this molecule, each point on this molecule is attached to 2 other carbons, then the free rotation about the single bond is no longer possible, because you don't have any point on this molecule where one carbon is attached to only one other carbon. When dealing with straight chain alkanes, whether it be ethane or butane or propane or whatever, you always have, for example, one terminal carbon. So if we draw, I don't know, propane with 1, 2, 3 carbons, you have a terminal carbon here and a terminal carbon here, and both of these terminal carbons basically have free rotation about this single bond. But on this cyclohexane molecule, we can observe that each carbon is attached to one. If we take carbon number 4 as our reference, each carbon is attached to one carbon to the left of it and one carbon to the right of it. So how does that fact change the conformational analysis of cyclic compounds such as cyclohexane? Well, in order to know that, we have to start viewing this molecule in 3D space from different viewpoints and perspectives. Right now, we're looking at this molecule in only 2 dimensions. We're basically looking at it from the top view in 2 dimensions. If we were to look at this molecule in 3D, we would see a much different molecule, and the reasoning for that is because although every hexagon and cyclohexane does take this geometry or does incorporate this geometry into its final form in 3D space, since each hexagon just naturally has a 120-degree inner bond angle for any one of these angles here, since hexagons like to have that geometry, and since each of these represent a carbon that does want to express the tetrahedral 109.5 degree geometry, what we see when we look at this molecule in 3D space is more of a hybrid of a hexagonal geometry and the tetrahedral geometry that each carbon wants to express. It was actually thought that the molecule resembles something like this, which in organic chemistry we call a benzene ring, which differs from a cyclohexane ring, and I'll explain why later. But as of right now, just pretend that this would be how cyclohexane would look in 3D space. What is wrong with this picture? Well, we have the hexagonal 120-degree angles here from this bond to this bond, and this bond to this bond, and so on and so forth. But what we aren't showing is that even though these carbons are bonded each to one other carbon, if we label this as carbon number 1 and then carbon number 2 and then carbon number 3, we see that carbon number 1 does have a bond to carbon number 2 and carbon number 3. And that fact does indeed restrict carbon number 1's ability to take the shape that it wants to, namely the tetrahedral geometry that we talked about in earlier videos. But it doesn't suppress it completely. And so this carbon number 1, can move up, or it can move down, or it can kind of wiggle about and express itself as closely as possible to the preferred tetrahedral geometry. So even though cyclohexane does in fact take a hexagonal arrangement when looking at it from the top view, if you're actually looking at it in 3D space, you're going to see that carbon number 2 for example, is going to start to kind of move over a little bit up higher, and this hydrogen is going to move a little bit down and to the, what is it, the right a little bit, so that we can get the textbook geometry of the tetrahedral molecule as closely as possible. I mean, it won't be exact, but they are going to try to take that arrangement. So we can look at it kind of as a mixture of both hexagonal geometry when looking at it from the top view, and tetrahedral geometry for each individual carbon that is going to be trying to express that geometry as much as possible. If we show you how the cyclohexane molecule actually is shaped in 3D space, it will look something like this. Okay? And this is from the side view, where each carbon has indeed tried to express its tetrahedral proclivities as strongly as possible. We're gonna move to a 3D view so that I can show you in more detail exactly what I'm talking about. Now, this is the top view of a cyclohexane molecule. This is what it looks like if you were looking at it directly overhead. But I'm going to rotate this molecule, and we do see the hexagonal shape. We see these 6 carbons forming a hexagon with their hydrogens kind of jutting out on each respective carbon. I'm going to now rotate this so that we're seeing it in 3D shape, and then you'll be able to see what I'm talking about when I say that it's kind of a hexagon on the top view, but when we move it, it takes tetrahedral geometries as strongly as it possibly can. So here we are starting to rotate this molecule, and we're going to start to see the tetrahedral shape appear. Alright, and this, now you can see that each carbon has kind of taken this tetrahedral geometry as strongly as possible. And this is what we call the chair conformation of cyclohexane, and it's the most stable conformation of cyclohexane, where each bond angle is as close to 109.5 degrees as possible, and they're actually at 111 degrees in the cyclohexane chair conformation, which is pretty close to the optimal geometry that each carbon wants to take. And so this is the most stable conformation of cyclohexane, and there's another chair conformation that is simply the inverse of this chair conformation, and a whole bunch of intermediaries between those two appear. Molecules are always moving about and are in perpetual motion, and since these, as we've seen before, since every carbon on a cyclohexane molecule is bonded to 2 other carbons, it can't freely rotate, like I said before, but it can move in ways that we call ring flipping. Cyclohexanes exhibit this phenomenon called ring flipping, in which, if we're looking at this leftmost cyclohexane chair, where each of the red hydrogens are pointing either up or down, what happens is, through a process called ring flipping, these red hydrogens pointing either up or down then become, on chair number 2 over here, the hydrogens that are painted in blue. They kind of switch to the position of an kind of an equatorial plane of the cyclohexane molecule. This process of ring flipping is achieved because these hydrogens obviously want to repel each other as much as possible, and since they can't freely rotate, instead of doing so, they are in this constant alternating form of the cyclohexane chair. And these alternating forms are arrived at through a process of intermediate changes in the cyclohexane molecule. All molecules seek the lowest energy configuration that they can possibly achieve. And these intermediate forms of the cyclohexane molecule that cause this ring flipping process to happen are much higher energy than these default standard chair configurations of the cyclohexane molecule. So we don't call these intermediates, these intermediate configurations that cyclohexane takes, as actual configurations. We look at them kind of more as transitional arrangements in 3D space that they take in order to flip to their alternate chair form. Now, there are many names for these intermediates. They take on the name of half chair, boat configuration, inverted boat configuration, but all you really need to know is that if we start with chair number 1 over here and chair number 2 over here, the intermediates that arise out of this ring flipping process are always going to be much higher in energy. We see this intermediate here. Now the potential energy of this intermediate of the cyclohexane ring flip is about 10.8 kilocalories per mole higher in potential energy than its original chair form. This second intermediate is a little bit less higher in potential energy than the default cyclohexane chair, but then it goes back to an inverted intermediate, which is still 10.8 kilocalories per mole higher in potential energy, and then it finally descends back to the inverted form of the second chair. And I want to actually show you the process of this happening, of cyclohexane flipping from one chair form to its other equally stable but opposite chair configuration. Before I do show you the ring flip animation, since cyclohexane is such a complicated molecule, we do need a way of kind of accounting for each hydrogen on this molecule at any given point in time. And the way we do that is by imagining a plane in the middle of this cyclohexane molecule so that we can account for any of the 12 hydrogens on this molecule throughout the process of the ring flip. So if we could imagine drawing on each of these carbons kind of little green circles so that we can then kind of connect 4 points on this molecule in this manner. Now we kind of have a rubric or a template or a position of reference, if you will, so that every hydrogen can kind of be compared to this point of reference. And so we use this plane in the middle of this molecule to define each one of these hydrogens on that molecule by calling them either axial or equatorial. And so first I'm going to explain the equatorial hydrogens. Basically, looking at this plane inside this molecule, we can identify hydrogens based off whether they're shooting kind of straight up or straight down away from this plane, or we can identify them based on whether they are kind of jutting upwards in a slant like these blue hydrogens are, or downwards in a slant like these other blue hydrogens are. So basically, when I say an equatorial hydrogen on the cyclohexane molecule, what I mean is any of these color-coded blue hydrogens that are either kind of going at a slant down away from the plane or kind of jutting up at the same amount of slant, just in the opposite direction, upwards. And so these hydrogens on the cyclohexane molecule, we denote them as equatorial hydrogens, and depending on whether they're going down away from the plane or up away from the plane, we will refer to them as equatorial up or down. So in this case, since this hydrogen is jutting upwards out of this plane, we call this an equatorial up hydrogen. And this hydrogen here would be an equatorial down. Now, for the red color-coded hydrogens, we refer to those as axial. We refer to this red hydrogen as an axial hydrogen. We refer to this one as well as an axial hydrogen. But depending on whether or not they're pointing up or down, we refer to these from here on out as axial up, or I'm sorry, in this case axial down, or axial up. So now we have some way to identify each hydrogen on this cyclohexane molecule in a way that we can account for them during the ring flip with a good degree of accuracy. And this is the convention in organic chemistry. I'm not just giving you my formula for memorizing these things. This is how we actually refer to them in the nomenclature of organic chemistry. So we can use that template to draw the cyclohexane molecule as well. So we can draw the basic form of the cyclohexane molecule, and we can start with the axial up hydrogens going first up, then down, then up, then down, then up, then down, and then we can draw the equatorial going first down, then up, then down, then up, then down, then up. And that's how we draw cyclohexane molecules. I'll kind of spread that out for you. I mean, you know, it's not the best artwork, but you understand. So now we're looking at a cyclohexane chair with the blue hydrogens in the axial position. I'm going to hit pause on the animations and we're going to try to follow the intermediates from chair to chair. I hit pause and now we're seeing the blue hydrogen starting to change. We get the half chair configuration, now the twist boat, the boat to the other twist boat, and now to the other half chair. And now we're going to see that the blue hydrogens have moved to the equatorial position, and that is the process of the ring flip. The blue hydrogens have moved from axial to equatorial. Once again, we started with the blue hydrogens, in which are shown here, and the process of the ring flip caused us to go to this position where the blue hydrogens are now in the axial positions. Watch it again and see if you can see it for yourself.